Hi folks, I'm Adam B., your machine tech instructor. In this video, we're going to explore steel metallurgy, a topic I find endlessly fascinating. By now, you should have already watched the case hardening video, which describes the step-by-step process we use for heat treating precision tools before grinding. This used to be a pretty popular video back in the day, and it got a lot of comments on YouTube, some of them more sensible than others. What I took away from most of them is that there's a general lack of knowledge about basic metallurgy, resulting in many simple questions, as well as quite a few unsubstantiated opinions and even purposeful misinformation. The goal of this video is to partially address this deficiency and raise the level of discourse. I have neither the desire nor the ability to train metallurgists and material scientists. I'm actually going to do my very best not to show you any graphs or equations or any of that stuff, but I do want to train informed machinists who have a profound and intuitive understanding of the processes they work with on a daily basis. I want you to grok this stuff. So let's get started. First, we'll define hardness, starting from our everyday lived experience and then zooming down to the atomic scale. Second, we'll define steel as a material, how it's made and what it's made of. Third, we'll define the phases or atomic configurations of steel and how you can identify them using a microscope. Fourth, we'll briefly outline the most common heat treatment techniques. Finally, at the end of the video, we'll look at some images of steel samples taken with a microscope. When people think of a material that's hard, diamond usually comes to mind. It's famous for being the hardest naturally occurring substance, although it has other amazing properties besides that. It's difficult to scratch a diamond, but you can use one to scratch any other material. Hardness then relates to how easy it is to deform the surface of a material. In general, harder materials tend to also be stronger, meaning that it's more difficult to squeeze, pull, or bend them to change their shape and break them. Although this usually also goes hand in hand with increased brittleness. Once the material starts to deform, it usually fractures shortly thereafter. This is exacerbated in diamond because of the way it cleaves. You can shatter a diamond by hitting it with a hammer. In any case, we're here to talk about steel, which, like all metals, is a ductile rather than a brittle material. Ductile materials deform in three modes when an increasing pressure is applied to them: elastic, plastic, and fracture. For example, if I apply a small amount of pressure to this paper clip, it'll bend. But then it will spring back like a rubber band to its original shape when I remove the pressure. This is elastic deformation. If I apply a little more pressure, I can bend the paper clip and it will take on the new shape. This is plastic deformation. And if I apply even more pressure, I can get the paper clip to fracture completely. In this case, I actually have to bend it back and forth a few times to work harden it before it will fracture. This steel is pretty soft. The pressure at which a material goes through these three modes depends on the unique properties of that material. Let's do an experiment. This is a half-inch square bar of 1045 steel, which is a plain steel with 0.45% carbon. It's considered a medium carbon steel. Here, it's in its annealed or softened state. I'm going to try to bend it with a hydraulic press. Watch what happens. As I feed the ram down, the pressure increases and the steel starts to bend. The top of the bar is getting squeezed together or put in compression. The bottom of the bar is getting pulled apart or put in tension. The pressure stays pretty constant as the bar bends more and more. In fact, it bends all the way to 90 degrees before a fracture opens up on the bottom side. At this point, the pressure drops to almost zero as the bar just splits in half. Let's try another one. This is a piece from the same bar, but this time I hardened it. Watch what happens. It takes twice as much pressure to bend the bar, but when that fracture on the bottom opens up, it's only for a second before the material snaps in half, releases all that energy, and goes flying across the shop. Let's watch that again in slow motion. Whoa, I'm glad I was behind a plastic shield for this one. Well, I think the experiment matched our expectations for how softer versus harder materials behave. Let's put all this together into a working definition of hardness. Hardness is the ability of a material to resist deformation from indentation, scratching, and cutting. Hard materials are also usually strong, but brittle and not ductile. To understand the cause of these macroscopic properties, we have to zoom in to the microscopic level. This is the surface of a piece of steel blown up 400 times. There's some interesting microstructure here that we'll be talking about later, but right now we need to go deeper. How about 100 million times magnification? There we go. That's the atomic scale. Here we can see the individual nuclei of iron atoms jiggling back and forth, with electrons angrily buzzing around. The important thing to note here is that the atoms are all arranged in a neat, ordered, and repeating pattern. That's because steel is a crystal. As a liquid substance begins to turn into a solid, the atoms or molecules come together, attaching themselves to a nucleation site and gradually building upon it. They form a regular repeating pattern as more atoms or molecules join the structure, essentially sticking to each other like Velcro through chemical bonds. To be specific, metals bond when neighboring atoms share their outer electrons. It's actually not as strong of a bond as, say, a covalent bond, which is the kind of bond in ceramics. The comparative weakness of this bond is actually what makes metals ductile. Here's an animation of atoms coming together to form a crystal structure. There's a sort of seed atom that acts as the nucleation site. Then other atoms start to bond to it and the crystal grows. Notice, however, that the structure is not perfect. Depending on how the atoms arrange themselves, there may be little spaces where an atom is missing. This type of point defect is called a vacancy. There are typically many of these nucleation sites, and so there are many crystals forming at the same time. When these crystals run into each other, they essentially run out of atoms and they stop growing. But they don't form one continuous crystal. Instead, they form individual crystals which are slightly misaligned relative to one another. These are called grains, and the lines which form between neighboring grains are called grain boundaries. So this is another type of crystal defect, a planar defect. These two defects are actually really well illustrated using an old executive desk toy from the 1960s called Atomix. This is my cheap DIY knockoff. There are 3,000 bearing balls between two acrylic plates. Imagine that each one of these balls is an iron atom. When the toy is horizontal, the balls are free to roll around. This sorta simulates a material in its liquid state. When the toy is tipped more vertical, the balls all lock in together like a crystalline solid. However, if I use a backlight, you'll see clearly that not all the balls are aligned to one another. There are some conspicuous holes, which are like the vacancies in a crystal, but more importantly, there are large groupings of balls that are neatly packed in next to each other, but each grouping is slightly rotated relative to the adjacent ones. So instead of one consistent pattern throughout the whole crystal, there are many individual grains with noticeable boundaries where they meet. Pretty cool, right? Let's revisit the three modes of deformation from earlier: elastic, plastic, and fracture, and observe them now at the atomic scale. A single two-dimensional plane of atoms forms a grid called a lattice structure. If we could push the top and bottom of this grid in opposite directions, the atoms would stretch away from each other, but the bonds would be unbroken. So if we stopped pushing, they'd return to the original grid pattern. This is elastic deformation. Now, what if we could push a little harder? And notice that there's a column of atoms here that seems to be out of place, jammed between two other columns. If we push hard enough, the atoms will stretch, form new bonds with other atoms, and actually rearrange their pattern. If we stop pushing, they will not return to the original grid pattern. They have taken on a new shape. This is plastic deformation. That extra column of atoms is a linear defect called a dislocation. You should think of plastic deformation as what happens when these dislocations zip and unzip themselves as they move through a material and rearrange the atomic order. Just for completeness, If we push even harder, we can separate the bonds between atoms along an entire plane. One piece becomes two, and fracture has taken place. But let's go back to those dislocations. We can now write a technically precise definition of hardness. If, as stated earlier, hardness is the ability of a material to resist plastic deformation, and plastic deformation is caused by dislocations moving through a crystal, then hardness is the ability of a crystalline solid to block the movement of dislocations. Think about that for a second. Literally anything that hinders the movement of these dislocations results in increased hardness. For example, dislocations don't like to move across grain boundaries, so refining a material so it has smaller grains will make it harder. Another way to do it is to intentionally generate so many dislocations that they all impede each other's movements. I call this the Three Stooges effect, based on a running gag from the old TV show that it's difficult for them all to fit through a door when they're all trying to go at the same time. This is actually what happens when you work harden a material, common in nickel alloys like 300 series stainless steels. The other way to stop dislocations, and the one that we're going to focus on, is to wedge other types of atoms in the spaces between the bulk crystal atoms. The extra atoms don't quite fit, and so they distort the lattice structure. We may consider these to be impurities, but this is also why adding alloying elements will always make a material stronger than when it's just a pure single element. There are two ways that these extra atoms can wedge themselves in. They can be substitutional, meaning that they replace an atom of the main bulk crystal. This is like how nickel substitutes for iron in some types of stainless steel. They can also be interstitial, meaning that they occupy the spaces between, the interstices of, the atoms in the main bulk crystal. This is like how carbon dissolves into iron to make steel. Let's talk about steel, this magical material that's so ubiquitous in our modern world. As already mentioned, steel is an alloy of iron and carbon. There are usually other elements in the mix too, sometimes as impurities and sometimes purposely added as alloying elements, which can greatly affect the mechanical properties of the resulting steel, but fundamentally it's iron and carbon. And it only takes a dash of carbon to do the trick. Low carbon steel is usually around 0.2% carbon, and even high carbon steel is usually only around 0.8% carbon. Only occasionally will a steel have over 1% carbon, and anything over 2.14% carbon is considered cast iron rather than steel. An iron atom has a diameter of approximately 0.25 nanometers. A carbon atom has a diameter of approximately 0.14 nanometers. These are incredibly small values, but what I want you to see is that a carbon atom is 57% the size of an iron atom, which turns out to be the perfect size to fit between the iron atoms in the crystal structure. How do we get the iron and carbon in the first place, and how are they mixed? Iron is mined out of the ground as iron ore, a mineral called hematite. This is iron oxide, basically a form of rust, Fe2O3. This ore is then smelted in a blast furnace with carbon-based fuel like coal or coke. Carbon monoxide from the fuel reacts with the iron oxide to form iron with a bunch of extra carbon in it, like maybe 4%, and then carbon dioxide as a byproduct. This pig iron, as they call it, can be poured into a mold and then it becomes cast iron. Or it can be reheated and blown full of oxygen. The oxygen reacts with the carbon in the iron to produce carbon monoxide and leaves just the iron behind. Using a similar process, a precise amount of carbon can be added back into the iron to achieve the desired concentration. And now you have steel. One of the things that makes steel unique is that it has multiple phases. These are different microstructural arrangements of iron and carbon. Part of the reason that steel can arrange in different phases is that iron is what we call allotropic. I think that's how you pronounce that. Meaning that it can exist in multiple physical forms or atomic configurations. The other reason is that carbon is the perfect size to fit between the iron atoms in those configurations, as already mentioned earlier. Let's take a look at these phases. Imagine that we start with hot, molten, liquid steel. As it starts to cool and solidify, it will form crystals in the way we've discussed already. The first type of atomic configuration will be what's called austenite, or gamma iron. So far, we've only been looking at single layers of atoms in a crystal lattice structure. But in order to understand the different phases, we need to think in 3D. I'm going to go ahead and construct a model using an acrylic box and some painted foam balls. These silver balls are iron atoms. If I start placing them one by one into the box, they form a layer on the bottom. And they naturally make a pattern with one atom in each corner and one in the center. Now I'll add another layer. These atoms naturally want to nest in between the atoms in the bottom layer, and I can only fit 4 atoms in the second layer. Now I'll add another layer. These atoms are sort of the mirror image of the first layer. I can fit 5 of them in there. Now, this is just a single unit cell, the minimum indivisible structural unit, but you can imagine continuing to add more atoms layer by layer in all directions on all faces to build up the material. This structure is called face-centered cubic, because it's shaped like a cube with an extra atom in the center of every face. Thanks to the specific way in which iron atoms pack together in the face-centered cubic structure, there are lots of spaces for carbon atoms to smush between them. The black foam balls are standing in for carbon atoms here. Austenite can dissolve up to about 2.1% carbon. This is the saturation limit for carbon in iron. Any excess carbon beyond this could not dissolve and would form clumps of pure graphite inside the material. It would no longer be steel, but rather cast iron. And if you look at cast iron under a microscope, you'll see the graphite. It's kinda like this mason jar full of water and salt. There's so much salt in here that the water has dissolved all the salt that it can. It's saturated, so no matter how much salt I add at this point, and no matter how long I leave the salt in there, believe it or not, I've kept this jar for 10 years, the excess salt will never dissolve into the water. But it gets more interesting. As the steel continues to cool toward room temperature, it will go through a phase change. It will form a second type of atomic configuration, ferrite or alpha iron. I'm going to construct another model, using a slightly smaller box this time. If I start placing iron atoms one by one into the box, this time the layer that they form only has 4 atoms, one in each corner. There's not enough room to fit a 5th one in the center. Now I'll add another layer. It turns out I can only fit 1 atom in the second layer. It nests right in the center of the 4 atoms in the bottom layer. Okay, I'll add another layer. Again, the third layer is a mirror of the first, with 4 atoms, 1 in each corner. This structure is called body-centered cubic, because it's shaped like a cube, with 1 extra atom in the center of the cube, or the body. Since the way the iron atoms pack together is slightly different in the body-centered cubic structure, there are fewer spaces for carbon atoms to smush between them, and perhaps you can see that even a single carbon atom distorts the lattice structure dramatically. Ferrite can only dissolve about 0.02% carbon. Now, you may be wondering, if we can dissolve up to 2.1% carbon in austenite, but then when we cool the steel down and it changes into ferrite, it can only dissolve 0.02% carbon, then where does all that carbon go? Once again, it precipitates out of solution, except that instead of forming pure graphite, it forms a ceramic compound called cementite. This is iron carbide, similar to the tungsten carbide we use for cutting tools. Now, the iron carbide doesn't come in clumps. Instead, it appears under a microscope as a remarkable lamellar or layered structure of alternating bands of ferrite and cementite. This structure is called pearlite because it looks a little bit like mother of pearl. Now, it should be said that ferrite and pearlite are what form from austenite when it's cooled slowly. But what happens if you cool it fast? Then you get what's called Martensite. This is essentially an oversaturated or supersaturated solution of carbon in austenite. There's not enough time for the carbon to precipitate out of solution, so it remains in the crystal lattice, heavily distorting it. The Martensite unit cell gets stretched into a body-centered tetragonal structure. If you look at it under a microscope, Martensite often appears as these needle-like shards. The important thing about Martensite is that it is exceptionally good at blocking dislocations from moving through the crystal. Therefore, steel with a lot of Martensite in it is very hard indeed. It's the stuff that makes hardened steel. Okay, so now that we've reviewed all those phases, we can put it all into practice. Let's think of some basic heat treating techniques we can use to manipulate the physical properties of steel to suit our needs. If we want to soften steel, we simply need to raise it up to the temperature at which it changes into austenite. I guess I didn't mention that these processes are reversible. They are, and you can go back and forth as many times as you want. Raising the steel to the austenitizing temperature is kind of like shaking an Etch-a-Sketch to reset the crystalline structure. Really fascinating stuff. Anyway, if you then cool it slowly, very slowly, maybe over the course of several days even, then you will have annealed the steel. On the other hand, if we want to harden the steel, and there's sufficient carbon in it to form martensite, then again we need to raise it up to the austenitizing temperature and then cool it quickly. We do this by quenching it or dunking it in some kind of fluid medium. It's usually water or oil. This is often followed by drawing or tempering to reduce stresses caused by martensite transformation. This involves raising the temperature of the steel back up to a temperature that's below the austenitizing temperature so no phase change will occur, maybe 400 to 1000 degrees Fahrenheit, and then holding it there for some length of time, perhaps an hour. Now, what if we want to harden low-carbon steel? In essence, all we need to do is add some carbon to it, and then we can process it as usual. We need to raise it up to the austenitizing temperature inside of a carbon-rich environment, like the box filled with charcoal in the pat carburizing process we use to make our precision tools. We hold it there for some amount of time, depending on how deep we want the carbon to diffuse into the outer layer of the steel. Then we cool it rapidly by quenching it. These three heat treating techniques are the most common ways to manipulate the physical properties of steel using heat. If you understand how they work, they will take you very far. Before we break, I'd like to show you some microscope images. I've been showing you a lot of diagrams and animations, which I hope were helpful, but there's nothing like looking at a real-life example. These are some steel samples that we prepared in-house. They show the different stages of the case hardening process as we do it here in the department. Preparing a sample is a multi-stage process. You must first grind and polish the surface, and then you must etch it with some kind of reagent. For steel, it's typically nitol, a nasty cocktail of 10% nitric acid in ethanol. This attacks the grain boundaries, highlighting them and other microstructures on the surface. Here I've got two samples, both of which have been carburized for 8 hours, but not heated and quenched, so both of them are in their annealed state. They are not hard. The only difference between them is that the one on the left has not been etched with nitol, and the other one on the right has been. Hopefully you can see that the etched sample is darker, but more importantly, there is a well-defined ring around the outside edge. That ring is the case of high-carbon steel. We'll be able to see a lot more if we look at it under a microscope. This image is really densely packed with information. The edge of the material is on the right-hand side. This is where the case is. On the left side of the image is where the core of the material is. Notice that in the core, we see a lot of white with a few splotches of brown. The white is the ferrite. It doesn't really look like anything special under the microscope. The brown, however, is pearlite. If I zoom in a little closer, you can make out some of the lamellar structure. If you count all the ferrite and pearlite together, the core is still only about 0.2% carbon, which is how much was in this low-carbon steel to begin with. So this is basically what the entire sample would have looked like if we hadn't carburized it. But as we move rightward into the case, we start to see more brown splotches until right about 1 millimeter, 40 thousandths of an inch in from the edge. At that point, everything turns brown. This means that the structure is 100% pearlite. Now that only happens when there's exactly 0.76%, let's call it 0.8% carbon. As we keep moving rightward through the case, we see some white beginning to emerge again. But this time it's appearing in between the grains. There's so much carbon now, 1% or more, that the cementite cannot all be captured in the pearlite structure. Instead, it forms in the boundaries between the grains, and that's why it's called intergranular cementite. So we can tell a lot about the composition of this steel sample just with a quick glance. Okay, now this is the same sample after it's been heated and quenched. Quite a different structure. There's Martensite everywhere. You can see the familiar needle-like shards. This is a higher magnification than the previous image, by the way. One thing that's worth mentioning is that the edge of the sample is now completely white, up to maybe 0.1 millimeter or 4 thousandths of an inch from the edge. This is the decarburized zone. When we were carburizing the steel, the low-carbon steel was in a high-carbon atmosphere, so the carbon tended to migrate from a zone of high concentration to a zone of low concentration, meaning the carbon diffused into the part. However, when we heated the part prior to quenching it to harden it, we had a high-carbon part in a low-carbon atmosphere, so the carbon tended to leach back out of the part. This results in the decarburized zone, a skin of almost pure iron stripped of its carbon. It's important to get through this layer to get to the hardened high-carbon steel underneath when surface grinding, so I always tell students to take at least 5 thousandths of an inch off every surface. Okay folks, that's all I've got. I hope the content in this video helps you make sense of the heat treating processes that we use in our department and more advanced heat treating processes you may use in the future. See you in the shop.